So we are talking about this controller, not the controller, the system. And we start with the open loop transfer function. And we have to do a lot with this open loop transfer function. And what you see, the open loop transfer function, this H naught, or H naught. And what you see that, this is the frequency response. And here in the frequency, and it's in decibel. And if you have the larger magnitude of the H naught, if it's larger magnitude, then we see that the closed loop transfer function which become 1. So this means Y, this output divided by the reference input, become 1. This means what we are giving in the reference, we are getting in the output. It's very smooth. You are giving this reference and you are getting. Very straightforward. But what happened at this region, when the magnitude is very small, this means H naught is very, very smaller than 1. So if you put H naught very, very smaller than 1, then what you are getting, then 1 is here, much larger than this part. Then you have the denominator part, which is 1, and the numerator part is only H naught. So you have the closed loop transfer function H naught over HF. This is like this. So what does that mean? That means we have now M, the closed loop transfer function, that we got H naught over HF, and which is Y divided by Y ref. This is the YS is the, And then you can write the output here, YS, which is H naught divided by HF. Maybe you can consider HF, this is the low pass filter, you can consider is 1, and you have only H naught and Y ref. So what you see here, you have the output, which is multiplied with the open loop transfer function with the reference. Since this part is very, very small, less than 1, and what you are getting, the output is much smaller than the reference. This means it's not tracking. So if you set the speed here, like this, you set the speed from this point you set here, since at the lower magnitude, and you will see something like the output maybe like this. So you can see there are much large deviation. So when we design the control system, then we try to design the controller parameters such a way that we could have the higher magnitude of the H naught after this omega. So we can try to shift this omega c as much as possible. So we can have the larger magnitude of the H naught. But it's not always possible to have this larger omega c, because this also depends on some other parameters. We will see what parameters impact the magnitude of this H naught. So when we derive the closed loop transfer function, we consider that we neglect this part, the disturbance part. Now we also want to see the impact of the disturbance. When we want to see the impact of the disturbance, and then we neglect the input part, this reference part. So if we neglect this reference part, and then if you derive the transfer function, and then you will find the transfer function like this. So this is the transfer function you get considering the disturbance. So one important thing here, you will see that what is the impact of this disturbance. And if you have a very larger H naught, what do you see? Then this one is neglected. And you have this H naught, which is very high. Then if you consider this HB over H naught, which is very small, because this H naught is very big. So HB over H naught, which is very small, and then output you will see that multiply the smaller value of this disturbance. This means which is very negligible. This means if you have the large value of this H naught, then you can damp the disturbance here from the system, and we will not see the impact of this disturbance there. So we can see also the impact of the disturbance, and another important thing, system stability. So we have the control loop, and we want to check the stability of the control loop. So how we can check the stability of the control loop? Now we go back to the original equation, original closed loop equation. So this is our original closed loop equation, and we have this not S, and we knew that S we can write in the frequency domain, we can write it S equals to J of omega. This means we can replace this S with J of omega. So we replace S with J of omega, and for certain value of frequency, you might get H naught, which is -1. This -1, what does this means? It means the magnitude of the H naught would be 1 at this point, and the frequency and the phase would be 180 degree. H naught J omega, at this condition, you are getting -1. When you have the magnitude 1, this means 0 decibel, 0 decibel, and the phase is -180 degree, that gives us -1. So what will happen if we have the -1? And if you look at through this transfer function, we now write it as J of omega, and we have the H naught, now we can write as a -1, and we have the 1, -1. So what you see, 1, -1, you have the denominator is 0. So now you have the denominator 0, then you are getting this output is infinity. So for a particular reference, now we are giving the reference here, Y ref, and what is the output for this condition? The output is infinity. This means unbounded, not in a limit. So we don't want that. This infinity means is unstable system. So we always try to avoid this condition when it's 0 decibel, and we don't want it to be -1 here. We don't want this condition. We always try to avoid this condition. So what we do, when the phase is 180 degree, then we try to have at least 6 decibel here. Instead of 1, we try to have at least 6 decibel, not 0 dB. That's how we can avoid the instability problem. So if we look at the frequency response of an open loop system, here this is an example. Here in this side, we have the frequency, you have the phase information, and you have the here magnitude, and this is the frequency, and this is the magnitude plot, and this is the phase plot. So what we are saying that we always try to avoid 180 degree when it crosses the 0 dB. This means this is 0 dB, magnitude 1, and in phase we don't want to have it at this point. So we always try to shift this position here, not at this point. So when you shift it, then you have the some phase margin. This is called the phase margin here. We try to have at least this phase margin to 45 degree. Sometimes you'll say 35 degrees, sometimes 40 degrees. Some people say 45 degrees. Let's say we can say it's 45 degrees. So we always try to have at least 45 degrees phase margin when it crosses the 0 dB. This is the one design rule, at least 45 degree. And then we can also check the gain margin. We check the gain margin when the phase plot cross the 180 degree point, 180 degree line. Here, this is the 180 degree line. And we check the magnitude here at this point from 0 dB to here. So we try to have this gain margin at least 6 dB. So this is a design rule to have at least 6 dB. So one example is given here in this plot. What you can see, we have, first we start with the blue line, and you can see that we have the 0 dB crossing at this point, and here we have this phase, and we have the some phase margin. Now for the same transfer function, this open loop transfer function, we increase the gain, proportional gain. Increasing proportional gain means increasing the magnitude. So we got the blue line by increasing the proportional gain, and we see that we are getting here higher magnitude, and it shifted here. But what about the phase at this point? You can see the phase information for the blue line. So you can see it cross at this point, right? The blue one, the green one, sorry, the green one, it crossed. And you can see the phase information is very small here for that. Maybe only a couple of degrees, maybe 10 degrees or something like that. So you can see we have the very small phase difference, but we don't want. A small phase difference means main oscillation. So we always try to avoid that. So the rule is to have at least 6 dB and 45-degree phase margin. So when you design, you need to remember this part. Any question here? So now we want to see frequency response of a PI controller. This is a PI controller, how this frequency response behave in the control system. In order to look at that, first we also check how they look like. Maybe they call asymptotic characteristics. So first, start with H0, which is only one integrator. If it's an only one integrator, and how the frequency response, this is the board plot look like for asymptotic, for integrator. If you look at for the integrator only, and you will see that for integrator, it would be like this one, the slope. Here we call the slope is -1 for integrator. So it's for this part. And if you look at the phase information, and you will see the phase for this, which is -90 degree. It's for integrator. It's only one integrator, and you will see the slope of this integrator, which is -1, and the phase is -90 degree. And the next one is the derivative term here, TDS. And for derivative term, and you will find the slope. If you look at the slope, and you will find the slope +1 is for derivative. For derivative, slope is +1. And if you look at the phase information, you will find it +90. So this is for the green one is for the derivative part. And then what about the low pass filter? And we have this low pass filter. And if you look at the low pass filter and how it look like. So now if we put the S equals to j omega for the low pass filter, S equals to j omega, and you'll see that for low frequency, it is 1/1 because T1 multiplied with j omega, which is very small, then it's only 1. So 1's mean is 0 dB. And after, when it reaches to frequency 1/omega c, cutoff frequency, then it's like this. So this one we are getting for this low pass filter. Because when the frequency is small, then this part is very small, then it's 1/1, and you can write it 1 means 0 dB. And if you also look at the phase information, for up to this part, it is 0, the phase, because it's only 1/1. And when after this part and the frequency, this part is dominant, then this one is negligible, then it's 1/, this T1s is like as the integrator, and you see that integrator phase is 90 degree, so therefore you will get the 90 degree phase, and slope is -1 because now it behaves like an integrator. So this is the board plot for a low pass filter. Now, if we look at the board plot of the PI controller. So now we have the PI controller and how it looked like for the PI controller. And you have the here one integrator part and here one plus TI plus. So we have the one derivative term and one integrated term. Then how it behave like? What would be the behavior of this PI? So if we want to plot it for the PI, and what you see when frequency is very small. If its frequency is very small, so it's very small here, then 1 plus Ti, this is a small part. So you can neglect this small part, is 1 over Ti, it behave like an integrator. So if it's behave like an integrator, then we will find -1 as like as integrator. So we can write is as an integrator with a slope of -1. And when it reaches this point, and then we can see that the 1 is now negligible. So if 1 is negligible, and then what you see, we have the TIS, and in the denominator we have also TIS, and this TIS, they are getting cancelled. If they are getting cancelled, then we have 1. So this would be the frequency characteristics of a PI. So what does this mean, a PI? So if we have something input, DC component, then you have the very large magnitude. This means it can amplify it. But if anything has here higher frequency, then it can suppress it with a higher frequency. So that's what we see here. And here, it should not be 0. When it's omega, then it would be Kp at this point. It's the Kp in decibel. So this is what we see for a PI controller. At the high frequency, at the low frequency, or in DC, you have a very high magnitude. Let's give a very good characteristics for this PI controller. And when it reaches to high frequency, then we see it's 1. And if you increase the Kp value, then it will keep the same position, but just like it will change the magnitude. If you increase the value of the Kp, it will keep the same structure, but it will shift because you are increasing the value of the Kp gain. And here is a -1 is because we are assuming Kp is equal to 1. So this is what it looked like for a PI controller characteristics. Now we have the basic about the control, PI controller, and how they behave and how they act when you have the open loop and the closed loop. Now is the time for us to tune this parameter, the Kp and Ki. So consider one open loop system. We have the H0 of a system that we previously presented. So we have the PI controller. The first part is the PI controller. And the second part here, not the second part, is the last part. Maybe we can move the Ks also here. This part is the process, is the plant. This Ks maybe assuming the power of this. Then you have the controller, the plant, and we have another function here, 1 plus T-sum S. So what is T-sum? We said that if it's a converter, then we need to have the PWM to turn on off the semiconductor devices, the switches. So we have the PWM and how we're generating the PWM comparing with the triangular, a carrier wave. So this carrier wave have a frequency, a period. So we have the one time for the carrier, the triangular wave. So we have the T-sum, which is coming one from the T-triangular wave. And also we see that we have the filter that we feed back. So the another part of the T-sum comes from the T-filter. Because we use a filter to remove the high frequency component. So now we have three components, one for the controller, and one for the carrier and all other things, and one for the process. And one thing you notice that here is like a low pass first order function. And here the T-sum, and it's come from the filter and also the carrier, and it's very small. If it's carrier, maybe they are 20 kilohertz, the carrier frequency, so it's very small. But this T1 comes from the physical system of the machine. Like if it's a machine, then you will see that you can represent it something like this. We have the B controllable out or B generated in this voltage in the machine. And then 1 over SL plus R. Here SL is the, let's say it could be armature inductance or armature reactance or armature resistance. So this is the one that you are getting here. T1 is L over R. That gives you T1 here. So now you have 1 plus T1 something and 1 plus this. And this T-sum is very, very small because you have the very high carrier frequency. And then you will see the dominant time constant is T. This T. This is the dominant time. Is the compared to this one is large. This T1. So this is the dominant one. So what we do in the modulus optimum tuning, what we try to do, we try to cancel this pole with that one. That 0. You have 1 plus Ti, yes. If we set Ti is equals to T1, there, then what's happening? You set this Ti, this is the Ti, controller Ti, is equals to process T1. If you set Ti is equals to T1, then you can cancel these two parts. So if you cancel these two parts, then what you have? So you're canceling this part and that part, and then you have the open loop transfer function, which is after removing this part, you have Kp, this is Kp and Ks divided by Ti, multiply with S, and S 1 plus T-sum. So this is your now open loop transfer function when you cancel this part. So we see that we need to tune two parameters. One is the Kp, and another is Ti. That's what we want to find. Now we set Ti is equals to T1, and the T1 comes from the system parameters. If it's a machine, then we know the inductance and the resistance of that machine. We can either measure it from the to calculate these values, or manufacturer, they provide these values. So once you have this inductor resistor, then we know the T1 here. So we know the T1, then we set Ti is equals to T1, so we got the integral time constant of the integral controller. So now we have the Ti, and only unknown is Kp. Now we need to determine the Kp proportional gain. Now we simplify, and then we got the open loop transfer function like this. And then if we derive the closed loop transfer function, then we come to this closed loop transfer function. Yeah, we know how to get if we have the open loop transfer function, GH, and the closed loop transfer function 1 plus GS, something like that. And also we have before one filter. Yeah. So this is just a simple control theory, and we come to a closed loop transfer function. And we see that our closed loop transfer function is a standard second order transfer function. And we have this characteristics equation. So once you have this characteristics equation, the second order transfer function, and we know a standard form of this transfer function. And the standard form of this transfer function is this one here. So you have the closed loop transfer function, and we can represent it in a standard form. Here we have 1 plus 2 sigma. This is the damping, and omega naught is the resonance frequency or the crossover frequency, and you have something like this. So we can represent this into like this, and then we know we can set this damping, like the damping for a yes.
What happens with the HF?
This HF. For now, you can the HF we are assuming part of the T sum. HF has a transfer function which is this HF, which is 1 plus TFS. This HF. And here we are assuming this TF is a part of the T sum. So it goes to this transfer function, this HF. So once it goes to the here, then we'll have the second order. Is it clear now, or?
That's okay, but I think it should be explained a bit quicker because it's very hard to follow when we do all these assumptions doing it and it doesn't say anything about it.
Yeah, thank you very much for asking the question. Yes. Yeah. So, yeah, TF, the filter, is a part of this T sum, so we represent just a first order transfer function by that. So now we have the second order, and then we have the standard form of this second order differential equation, and we see that we can represent it like this. So if you look at here, and we have this term equivalent to this, and this 1 over omega naught square, which is equivalent to that, so we can write it in the other side here. So we have the this resonance frequency omega naught, which we got 1 over. Okay, before that, we are setting this damping is a standard way to tune a parameter to set a second order differential equation. We put it 1 over square root of 2. So we put the damping 1 over square root of 2, and we already know this Ti, which is equals to Tu1. Then comparing this equation to that, and if we solve for Kp from this, and you will get the Kp like this, which is T1 over 2Ks multiplied T sum. And here we have all of them known. This T1 is known, it's come from system parameter, inductance and resistor. The Ks also the part of that, and the T sum, which come from T triangular wave and the T filter. So all these are known. Now you got also Kp by comparing this equation to that. So now if you insert this to the second order equation, and you will see that this transfer function has only, the closed loop transfer function has only T sum there. T sum part is only remaining. This means the response of the system closed loop transfer function here for a motor system is only depends on the T sum here. T sum is the delay that caused by the PWM signal and also the filter signal. So this means if you have the first higher carrier frequency and this high value, no, this means a smaller time step. This means it will be very fast. It will follow very fast. So we have one example here, response, T rise time for the closed loop, and we set a step response for the transfer function that presented in the previous slide. And we see that T rise time, which is equivalent to 4.7 times multiply with T sum. This means if we have the higher carrier frequency for the PWM and also higher cutoff frequency for the filter, low pass filter, then you are getting faster response. As high as this, then you are getting faster response. For this is a 4.7 times of T sum. Any question here? If anything, do you want me to repeat? It's not clear for the modulus optimum. Just interrupt me anytime if anything is not clear. So we use the modulus optimum criteria to tune inner loop controller. And one thing to remember when you apply the modulus optimum tuning is in this form. Here the process, the plant transfer function, which is 1 over T1 multiplied with S in this form. Once it is in this form, then you can apply the modulus optimum criteria. But what about if it's not like this form? If it's only one integrator, and sometimes you will find the process part only just an integrator, 1 over S. Like if you want to control the speed of the machine, and then you will see that this part, instead of 1 plus T1S, it will be only T1S instead of this part. So this means you have one integrator here and then another integrator there. Once you have this condition, then what will happen? We know that one integrator give us 90 degree, right? Minus 90 degree. And then another integrator give us minus 90 degree. If we assume the effect of these two cancel, then you have the minus 90, and two of them you're getting minus 180 degree. So we are trying to avoid minus 180 degree because we see that when it's minus 180 degree, then the system becoming unstable. So we always try to avoid that condition. So when we come to the part modulus optimum, I'll discuss this a bit more about the module optimum tuning. So here, what I want to present, we see that if we have the inner loop controller and we derive the transfer function for the inner loop controller, and it becomes a second order transfer function. So this is the second order transfer function. That's what we got for the inner loop controller. 1 plus something multiplied with S and something multiplied with S square. This is the closed loop transfer function for inner loop controller. And if you have the other outer loop controller, that also bring another PI controller and also something in the other side. This means if we want to consider all these things together, then it will be higher than second order transfer function. So if higher than second order transfer function is difficult to tune and it's not straightforward. So what we do, we try to have we try to apply the equal area criteria. This means if we have this original second order transfer function like the yellow one, and we try to approximate it. We try to check the area so that we can have something similar to that one, close to that one, but not exact. So what do you see if we have something like this yellow one, and we try to make the second order transfer function equivalent to a first order transfer function, that give us the similar area, similar behavior. So that's what we applied here. We have the original second order differential equation, second order transfer function for the inner loop, and we try to make it equivalent method, equal area method, and then we come up with a first order function. So you initially have the second order, then apply the equal area criteria, then we got the first order transfer function. And in the first order transfer function, we need to have this T equivalent. So how you get the T equivalent? Equals to this original parameter, and you will see that this T equivalent comes something like this, which is T1 divided by Kp Ks. So when we tune the outer loop, then instead of the second order transfer function, the inner loop will present with a first order transfer function. So we do it for the outer loop design, outer loop, when we tune the outer loop. And the controller that I was discussing, the modulus optimum, the design I presented is for the continuous control system. But now we implement the controller in the digital platform, like in the DSP, in the microprocessor. So when we do the design in the DSP, in the microprocessor, then we do the sampling. This means if we have any analog signal, then we need to convert them into a digital signal. Then with a sampling time, some with a particular time. Even though they are very fast, if we use the FPGA, they are in microsecond. Even we can program it also for nanosecond. They're very, very small time step. But still, we need to consider the sampling time. And in the compendium, it is discussed a bit more detail. So I'm not presenting here more detail. You might look at there the step how to do the discretization. Like if you have anything in the time domain, then you can convert them into discrete system. Or you can convert them into Z domain. And this is the method using trapezoidal method. And here, if you look at S equivalent to, originally in the S equivalent, which is like this. And we have the T as a sampling time. So this is the method. It has been discussed a bit more detail in the compendium, so I'm not discussing more detail here. But what I want to say that the sampling time has also an impact in the tuning parameter. So you can see we have initially the T-sum, and we said that T-sum is the part of comes from the part of the carrier signal, PWM carrier, and filter. Now, in addition, T-sum, it has also the part from the sampling. So the T-sum now has the carrier, sampling, and the filter, these three parts together. And then if you see after detailed derivation, then you will see that Kp would be like this, and the Ti of the integral time constant like this. So I just will simply present the symmetrical optimum. What I was saying in the modulus optimum, then we had 1 plus T1s. In some condition, you will see that it's only integrator, not 1 plus T1s. So now what do you see? As like as what it is in the modulus optimum, what about if we cancel this 1 plus T sum with 1 plus Ti sum? If you cancel these two parts, then what will happen? If you cancel these two parts, then what do you see in the denominator? You cancel these two parts. So if you cancel these two parts, that I was saying that what you have is only one integrator here and another integrator here in the open loop. If you have two integrator, 1 over s square, this means it's giving you minus 180 degree phase margin, minus 180 degree. This means it would always operate at this minus 180 degree at critical point. So the system will be unstable, and we don't want that. Therefore, we cannot cancel this with that one. When you cannot cancel this with that one, then you need to use the module symmetrical optimum tuning method. So how we do the symmetrical optimum tuning method? We select Ti, the integral time constant here for the outer loop, which is beta multiplied with T sum. Here beta must be greater than 1. So here beta must be greater than 1, could be like maybe 4 to 10, something like that. So once you have like this beta, and then what will be the frequency characteristics of this open loop transfer function? And if you look at the frequency characteristics of this open loop transfer function, and you will see that it will be something like, now we are plotting the frequency characteristics of this one. So in the beginning, and you will see that this two integrator is dominant at the low frequency, only this two integrator, because this is very small part and this is very small part, so you have only one and you have only one. This means you will have the slope something like -2. So you will have the slope something like -2 until Ti. Yeah, 1 over Ti frequency. And we know that 1 over Ti, which is 1 over beta T sum. Yeah, so it comes like this. And when it reaches to that point, then it will be, the slope will be 1 here, -1 at this point. The slope will be -1. And again, when you reach to the point T sum, this is the frequency 1 over T sum. And then it would be again -2. And this is the point, is the and this distance depends on the beta. So how long it would be -1, it would be it would be based on the beta that you are selecting here. So one example is given here. You can see here, this is the open loop characteristics. And if you also look at the phase information, and you can see that is the middle point. This is the middle point here. It's a 0 dB. And you will find the maximum phase difference. Otherwise, at these 2 points, you will find the phase is -180 degree. This means here you are getting phase which is -180, and then it's become 90 degree, and again -180. So this is 180 degree and -90 degree. And this is the point in the middle somewhere. So if you use the symmetrical optimum, and you are getting the point somewhere here with a very high phase merging. So therefore you apply the symmetrical optimum tuning method here. This is the one step response for, like, this is the speed reference that you want. And then a step response of this one, yeah, maybe I should also say that the closed loop transfer function with the symmetrical optimum is become a third order transfer function. Here we have the third order transfer function. And you can see that if it's a low pass filter, first order, then it should come something like this. But here you see that a small overshoot here, this part. And we have also some limit how much it could be. We allow is 1.6, but here it could be a bit more. Because of that, if you apply the step response, then you will see that this would be your step response. So you have the beta, which is 4, and you can see that more than 40% overshoot here. This is not expected. We don't want that much overshoot, but this is just to show an example how much the overshoot. For example, if you set the beta equals to 10, then you will get a bit different, maybe something like this. If you increase the beta, you will get less overshoot, like this. I think I'll stop here today, and I'll be here a couple of more minutes. If you have any questions, just feel free to ask any question, or if you want to know anything. Yeah, otherwise, thank you very much for joining the lecture today.